These are technologies that were developed in the late 80s. And if we want to continue a cycle where in 10 years' time we are applying technology, we have to have basic research as well. We have to go beyond these and find out the next generation. And what is really missing, and I think all the roadmaps point this out, is the next generation of shop floor automation. What will happen when the PLC dies? Why is our flexible automation so expensive? Why are we not adaptive? And this, I really hope, is going to become a little bit clearer to you during the day. And we will also present some of the project results that indicate one of the directions that one may go. For Express, we derived that we have to focus on rapid deployment of systems. I will underline this and detail this in the afternoon, what we mean by deployment. I'll tell you that you can build an assembly line for the car industry. It will take you about 4 or 5 months to build it physically. To get that assembly line running will take you a year. By deployment, I mean build it and get it running. And it has to be quick today. You don't have months. You don't even have weeks. And it has to become cost effective. We will need automation in Europe. We are getting older and we're not making babies. So we will need automation. And it has to become cost effective. Finally, product design and production system development have to be linked in a really effective way. When you change one, it will affect the other, and how it affects the other. Excuse me for the spelling mistake there. I'm just trying to see if you're awake. It's focused on the new human roles. With the advent of new automation, with the advent of more autonomous behavior from machines, the roles of the operators on the shop floor will change. And we have to capture their knowledge. And one of the guiding lights really in our thoughts was something Professor Westkamper said during the Manu Future road mapping. Really, we have to change our tailor thinking and to go into a situation where we can rearrange machines and operators as we like, when we like, at a minimum cost. So this is really the essence of FA3. And what I was saying before, it's fine. We have to get industrial commercialization, but it takes many years for research to become industrially viable, about 10 years. So it's no surprise that lean is coming to industry now. It's not surprising that some of these buzzwords are coming to industry now. But what do we do in research today that will come to industry in 10 years' time? That is the key. And that is where we have to create a link between applied research and basic or blue sky research. And I would say that Express really is the middle one there. We are trying to bridge blue sky research, or very, very basic research, which is coming from other projects, to the applied R&D in industry. And that's a more schematic view of how we see the Express objective. Internal projects. We have 3 main internal projects. We are defining at the moment a methodology whereby we can link product models that you do when you do the product design, to process models that you use when you're deriving machinery for the production floor. This is a project I will probably talk a little bit more about in the afternoon. Functional requirements from a human factors point of view. This is Professor Lena Mortenson's specific area. We have applied for a new FP7 project in this specific area, and I think we will have to do a lot in the future on this topic. It's a bit neglected at the moment, and we will try to point this out in the next talk. Third project is mechatronic reference architectures, and I will not say much more about it now. It's a project which has been ongoing for many years, and I will detail it in the afternoon. But this is about new production system equipment, which can configure itself. It doesn't need any programming and is highly modular. At the same time, We're also trying to keep the link with the other two areas alive. We have feedback all the time with FA1 because they're working with new processes and materials. One of the key issues in getting systems deployed quickly is to be able to input new processes quickly into the production line. So we're following that. And of course, business models. This is also a very new research area. When one of my PhD students started investigating on how much is known about business models for industry, he found out there's practically nothing. Decision making in industry as to what I am going to invest, when I'm going to invest it, and why, is an area which we really have to start thinking about. Okay, these are the internal projects. We have collaboration throughout Europe, both academically and industrially, beyond what Thomas showed you. Closest to us are Lisbon and Nottingham. We have also exchange with Karlsruhe. We have had student exchange with them in FA3. And industrial collaboration, I will actually leave it to Christoph Hanisch from Festa to detail that. But we have many projects that have been ongoing, in some cases, many, many years with these companies. So we're trying to bridge over to Europe as much as possible. So during the day, you will see projects presented, and I am only going to show you projects that have been created within the Express time frame. I think that if you go through the brochures, you will not see a lot of projects under FA3, and that's because we have avoided putting all of our projects. With 4 or 5 professors here, it would have probably covered the whole page. So we're only going to talk about the projects that have been created when Express came along. And they are the 3 areas: human aspects, product design integration, and metrology. In the afternoon, I will go through some European projects. Unfortunately, one of our speakers, Professor Barata, had some family problems, so I will take his speech in the afternoon. We will have Dr. Hanisch's presentation on the industrial perspective, and I hope by then you will have a clearer picture of FA3. So that's all for me today. I tried to be brief, as my dear colleague Thomas went over the timeline, but I hope that we can give you a good idea of what FA3 is. You can keep in touch with us, and hopefully you can join us, because we are going to be making more European and Swedish project proposals in the future, and the more we are, the merrier. So now I will leave the word over to Professor Mortensson. Let's see if I can help her. There you are. Voilà, madame.
Mauro was saying that we need automation in the future because we are not making babies. He's correct there. We are not making babies, but luckily our children are making babies. So there will be human beings also in the future production. Also, closer to the microphone, is that what you say? Okay. We'll see today, I think, a lot of examples of very modern equipment in industry. But the human being is the same today as 2 million years ago. So the challenge is to adapt technology to the talents of the human being. So that's what we'll try to do in our projects. So I will mention a little bit about human aspects. I will talk about automation. I will give examples from assembly work. Operator competence, something about change management, and I may end up in some conclusions. the system and its people. In one of the future projects, where Mauro is the coordinator, it's called My System. These are the building blocks to design, to build, to ramp up, and to have production. And the people in the different phases are designers, which are mostly engineers in the building process, engineers and operators in ramping up the system and the production, and also operators in the production. So how do we get a joint understanding for all these actors? In aviation, we are talking about collaborative decision-making. How do we give the same information to all actors in a system? And that is definitely something for production work as well. CDM is one of the future aspects. So what are the human aspects? Well, there are quite a number of them. Designing the product, issues like tools for the designer to do this. User-friendliness is, of course, one aspect. When it comes to design of the hardware, the production system, it's ergonomics aspects, it's the flow of production, the supply chain, but also the particular workplace for the individual. We then come to the question of what function should we give to the machine and what function should we give to the operators. And the roles and tasks for operators in assembly is something that I will come back to, but that's a very important part when designing new systems. The human-machine interface comes in somewhat later when we have decided what functions the operator should have. And that is a special research area. I will not go into that today, given the short time. Competence levels for operators are important. And then when introducing the new technology, this should be done in an appropriate way. Otherwise, it will not work independent of how clever the technology is. Automation and a theoretical background to automation. Billings is an American researcher, and he has formulated what automation can contribute with to the complex systems that we find in industry, that we find in aviation and elsewhere. He says that automation should manage information and present it in an easily understood manner. That is really a challenge. To integrate processes without coupling them in a way that the operator can understand what the automation is doing. And to keep the operator involved by informing about what it is doing, and also to provide decision and action options without limiting the operator to bypass them when needed. So this is what the system should do. This is what automation can contribute with. And then the human being has got a flexibility that the machine system has not. Also the creativity. The human being is able to find knowledge about the complete situation by using all available sources of information. In the cockpit, for instance, the pilot, he collects information from all the various instruments. In the production system, it's the same with the operator, and he can also use smell, for instance, to find out if something wrong is coming along. And the individual has got the ability to cope with incomplete knowledge and uncertainty. So these are the human contributions which should be taken care of. So what do you experience when you deal with computers? I wonder if you recognize questions like, what's it doing now? Why did it do that? What's it going to do next? How am I going to stop it from doing that? And how will I get it to do what I want? Anybody recognize these questions? From a simple system like the word processor. Well, this is okay when it is a word processor, it's okay with the production machine, but it may not be okay in a safety critical system. There's also another concept which is called automation-induced surprises. That is, if the automation does something which is a complete surprise to the operator. When there are particular facets of the software program which is not known to the operator. This is a very bad situation in safety critical systems, like what happened in the Gottröra accident in 1991, when there were part of software which was not known to the pilots nor to the airline company, which was SAS at the moment. Due to the basic knowledge of the pilots, they managed this accident very well. Right, so back to production. What are actually the operator doing? The concept of supervisory control comes from Tom Sheridan from MIT. He's put down this very simple model which works very well in all kinds of work. You have got different processes, and the computer is a task interactive computer as well as human interactive computer. And the operator, he's got 5 roles. He's planning what should be done in the system. He's teaching the system, programming it. He then is monitoring the system that things work out as they should. But they don't always, so he has to intervene when something goes wrong. And from all intervention, they learn something, and that knowledge could be used in the coming planning of the future work. So it's the intervention which is the main role for the operator of the future. If you look at assembly work, you could put it down. You can divide the roles into different tasks. So the teaching task means to program for a new product, for instance, material handling, order handling, setting up of the machines, and so on. So if you put it down into these very minute tasks, then you get a clear picture of what the human being does, and also how it can be supported by computer system. We can then add another dimension. So it's different levels of knowledge which is needed in the production system. The operator task in assembly system, like I've said, is to analyze the disturbance and to take actions. There's also the quality assurance of product and system. That it means to test the product. You may have to take actions like to disassemble the product and to assemble it again. Actions to prevent error to reappear, like analysis of the robot program. Maybe you should put greater demands on the supplier. And also statistical follow-up of disturbances, which is unfortunately not always done in production systems. If you ask the operator about this very important role of taking care of disturbances, they may say that what's most difficult is to detect that the disturbance has occurred, to know whom to contact, to find the cause of the disturbance, to describe the disturbance to others, and all to document the disturbance, and last but not least, to find out lasting solutions to prevent further disturbances. I've heard many operators say that we don't have the time to find out a lasting solution, so we are solving the same problem time and time again. We may solve the same problem 50 times, and which isn't a very clever thing to do. The competence for the operator is defined in this way. It means theoretical knowledge and skills based on experience, but it also means to have the right attitude and ability to correct judgment, and also to use the knowledge in its proper context. Asking the supervisors or production teams, they say that the competence development in the whole group is very important. You shouldn't only look at the particular individual. So the competence in the group, how many novices can you have in the group? How many experts do you need to make it a very efficient system? You should also have a plan for the individual and his competence development, and I think many companies have that. What is the basic and technical education for one or several persons in the group? And is it possible to inform or instruct people to replace education and training? You may have the idea that sometimes the software is designed in a particular way, so you don't need to train people, but that is not always the case. But finally, how to introduce new technology. You can have a very clever technical solution, but if it isn't introduced in the correct way, then it doesn't work the way you think it should. And I have now got a very old example of introducing new technology, and I know one person in the audience who's going to object, but I take the risk. This robot cell was introduced into a company some 10, 15 years ago, and it was a very clever robotic cell. It was actually designed in this department, and it was put into industrial application by an industrial company, and it was set up at Atlas Copco Tools in Tierp, and it would take some 20% of the manual assembly work. It was only that there were a few things that didn't work out quite well. As the intention was that the robot should do everything, so you don't need to train the people. That was not the correct thing to do. The operators were not involved in the ramp up of this robot cell. So there was a lot of agony against this equipment. And as the operators were not trained, they couldn't find, when everything came to a standstill, they didn't know how to find what was the cause of the disturbance, so they had to call the supplier, and he had to come up to this place and find and correct what was missing or why it didn't work. That took a lot of time when this robot cell didn't work. So the operators, clever enough, took back all the manual work. And, well, it's just one example of not training the operators properly. You don't get the outcome that you expect. So, finally, when dealing with large and complex systems, one always assumes that when things get out of hand, the operator will save our day, and that's the future. The operator will save our day. What do you think, Mauro? Thank you for your attention.
We will always need operators on the shop floor. The interesting part is that I think even in the other sessions today, you will hear the word self-learning being used. And I would like to raise a warning finger. There will be machines that start to learn by themselves. This is a lot more complex But when we do get there, then the monitoring and the learning phase will have to be done with a human being. Otherwise, you will get some really nice surprises. Okay, thank you, Lena. I think we can go over to Professor Vikander.
Thank you, Mauro. My talk today deals with one of the points that Mauro brought up in the introduction, namely how to integrate the design of the product with the design or configuration of the production system. I am spending my days in the neighboring department here, Department of Machine Design and the Mechatronic Lab. And the work that I present here is joint work between me, one of my PhD students, Asan Kwamar, who couldn't be here today because he's spending time at Georgia Tech in a world-leading lab there dealing with the same questions. And also Carl During, who is an adjunct professor in my lab from Mechatronic Laser System, and he's actually with us today. So that's the background, and this is also the Express initiative really brought the work we did before to a new, let's say, dimension, because we didn't look too much to the production of the products, but we had enough problems with integrating all the different disciplines that needs to be integrated in a product like this, which is actually a brake-by-wire component manufactured by Haldex, a Swedish company, which we are looking at as an example for what we are doing. So far we have looked at the design of the product, not so much about how this is linked to the production system. So this is a new activity actually taking place because we have actually Express now, and this is obviously a very important thing. So here we of course have a lot of different people to integrate to come up with a product like this and guarantee its performance, its safety, and so on. We have mechanical designers, we have control engineers, we have system designers, because this product then goes into a larger system. It's a brake caliper on each of the 4 or 6 or 8 wheels, depending on what kind of vehicle it is, and all this needs to be coordinated, it needs to be safe. It cannot fail in the sense that that Lena was talking about. I mean, why did it do what it did now? That's not the kind of question we want to ask from the brake system. And there's of course software engineers, and there's I don't know, more people involved to be able to design the product. But still, we haven't looked at the production of this product. So, and all these people need to be able to communicate and come up with the right design solutions, understand each other. How do I make the mechanical designer understand the software engineer in such a context, for example? And even more difficult than when we start to look about the production of the product. How do I link the people that are changing the design in the CAD view of this product to the capabilities of the production system or the assembly system? This is what we want to approach in this project. Okay, so maybe today it's quite a lot like this, that each of the discipline or each of the parts of the design team have a different set of documents, sketches, maybe some computer models that reflect the mechanical design or the software design or the control algorithms. But it's very hard, even though Lena said that the benefit of the human is that they can understand the whole. But it is not so easy actually to understand the whole. You need some system to support you when the products become complex. And here there are of course a lot of dependencies. So if I make a change in the mechanical design, it will definitely change what the control engineer has to do, which then the software engineer has to change in the software, and the electronics engineer has to cope with that so that the algorithm actually can execute on time when it is changed, and so on. So there are a lot of dependencies, and these become very difficult to handle when the system becomes complex. So there's a big question mark there that we are trying to straighten, and there's a lot of problems here related to communication between these disciplines, complexity of the products, and the different dependencies between the different parts of the design or parts of the product. So those are the things that we try to approach here. And this, as I said, is based on work that we have done before Express happened. But what we are now doing is to try to extend it to more parts of the complete life cycle of the products. So we're now trying to introduce manufacturing and production into this thinking. But the other 4 bullets here is the ones that we have worked with before. And other people in the mechatronics lab here at Kate are also working on the integration of software, electronics, and control. So there's quite extensive activities of how to link all this together. And the approach then is model-based. So we try to figure out, I mean, within the different disciplines, all these designers and people use models when they design their part of the product. So models for software development, model for control design, model for mechanical design, so on. So there are models already that you can that you can simulate, that you can draw conclusions from, you can analyze what you have designed, and you can predict the behavior of your part of the system. But it's more difficult to predict the behavior of the product, of the whole product, and over the whole life cycle. So for that reason, then, one of the main issues in this work is how to integrate models from different related to different disciplines, and then integration of different tools that are working on those models. So, and the approach that is taken here then is that which we are discussing, whether it's the right approach or not. At least this is the approach we have taken. So the approach we have taken is to have a system model that contains information of all the different aspects of the product. But this will never be enough because we will not be able to, from the same model, analyze all the different aspects. But at least we can capture the main things about the product in a system model. But for analysis of the different parts, we will need models of all the different aspects of the product. And this is then some of the research results that we so far have. We have an integration infrastructure for integrating models and tools reflecting different aspects of a product or a system like this. We call it a model integration framework. And then we go basically from a situation where the individuals are working on separate models, separate documents, producing separate results to a situation where all those things that are being designed can be somehow integrated. So not instead of, but as a complement to people talking to each other and trying to understand the whole of the product, we can also now link models of the product seen from this different perspectives to each other via this integration infrastructure. And what we have been starting with is linking the mechanical part of the design to the system design and to the dynamics and control design. So those 3 things we can now integrate in the developed infrastructure. And we are looking at the aspects of how to link this now to models of the production system. And this is ongoing work, so I cannot give you too much results. But maybe next time we meet here, we can speak about that as well. So actually, we go from this situation where we couldn't understand everything in between us to another situation where the models can, so to say, speak to each other. But there is still we still have these dependencies between. So if I do a CAD design and I have another team member doing a software piece, there will be a link between these two. So if I change in the mechanical view, there needs to be some kind of update in the software view, and so on. Same goes for the production, of course. If I change the configuration or the geometry of a mechanical component that should be picked by a robot for assembly, for example, there is clearly a dependency. So I cannot change in the mechanical design without maybe affecting the production system. Maybe it's okay because the gripper or whatever can handle both these designs, but I cannot be sure about that. So somehow these dependencies needs to be resolved. And the approach, which is quite new, that we are taking here is what we call dependency modeling. So in order to handle these dependencies between the different parts, we are trying to model the dependencies. And for example, if I have a mechanical component again, that is part of my control designer's work. So typically the control designer is only interested in the, let's say, the inertia or the mass or the inertia matrix maybe of a component. But from that, there is not a one-to-one mapping to the actual geometry of a product. The geometry of a product could take many different forms that has the same inertia matrix. So how do I handle this dependency in between these models? Okay, so therefore we have now designed this model integration framework using different kinds of tools. And as I said, we have integrated mechanical CAD design in this. We have integrated dynamics analysis via MATLAB, Simulink, and SimMechanics, and a system model using SysML. So these are the things that currently are running, at least as a prototypical integration. And I will not go into any detail about how this works, but work is being published about it right now. Robot arm, where we here see the CAD view, and we see the SimMechanics dynamics simulation view, and we see the system model in SysML, and what this can look like when you work with the system. And here are the models then in the different views. And there are some different pieces here. There is a Simulink connector, there is a solid edge parser, there is a magic draw connector, and so on, that connects all these things together. And those are components that have been developed such that we now can more or less automatically change a property of a model in one domain, in one view. And this change of this property then propagates via the SysML or system model to the other domains or other views of the product. And coming to the final slides, this framework is in principle generic, so you can add any kind of model framework or modeling tool to it. And then, of course, what we want to do is add, and this is what we are working on now, how can we link this to the kind of models that Mauro's team is using for configuring the production system. So this is what we are aiming at. And this was actually my next to final slide. So if you have some questions, I'm happy to answer. Yes?
What is the future enabling file format?
I don't know. I think the file format is one thing that we need to think about, but it's also one of the the approach taken here is based that we have what we call meta models. So for each of the modeling formalisms or tools, if you wish, we need a meta model. That is a model of how this tool is using modeling. And then we need such a meta model for each of the tools. And then we make sure these meta models are compatible, so we can interchange information between the meta models. And then there we need some kind of format, of course. But which format we use has not been of particular interest for us.
Actually, I'm happy to say that I belong to the family, because actually I'm working in the industry still. But I have a little of interest. When you get older, you want to check your brain if it's still working. So I'm a PhD student today under Professor Lars Marksson here. And I'm going to talk a little bit about metrology and why is metrology so interesting. And I have set some kind of message here that it's the road to outstanding metrology is the road to outstanding quality. I think it's really, really true. So that is what I'm going to talk about. First of all, why do we need smart metrology? Does anyone know that? Why do we need metrology? I think that is the first key questions that I think we should go into. And one reason, there are several reasons actually, but one reason is we see today that we go from production of large series to a production of small series dedicated for customer-oriented products. Actually, we are more and more having the interest on special products just for me. And that is, you can see that effect also in a lot of different applications. And I think that is one key thing here, that this is actually a change as this was before. We want to have a special kind of car that is suited for us and so on. So there are different that is one very big reason. Another thing is that for this reason, metrology is needed in the process, not only afterwards. That means that you're not interested just to know that this product is inside two tolerance limits, for instance, and you just check it afterwards. The thing is that there is a trend today, actually, that we are much more need metrology in the process for active process control. And I will show you I like this. So there's a story behind this, actually. I don't know if anyone has seen this plot before, but this story behind is that Sony is I think everyone knows Sony. That is a large company in Japan that, among other things, they make TVs. And some years ago, Sony put up a fab in the United States for producing the exact same model of a TV. And the thing was that in this situation, people didn't like to buy the American model. They preferred to buy the model that was produced in Japan. And ask yourself the question, why is it like that? You just look at the plot here, and you see that the American model was quite okay. It was inside the tolerance limits, so it should be okay. But if you see the difference to the Japan model, is that in Sony Japan really had a different approach in producing this TV. It's so obvious here. And let's say now what happens if you have this strategy that good enough is okay. If you now change, because of competition from Samsung, for instance, if you change the tolerance limits, it's just a little bit, who is the big loser here? And that, I think, is one of the things that is so important difference between the way we think and actually starting to change now, but as we have been thinking for many, many years in the Western countries, that good enough is good enough, and if you want more good enough, it costs more money. But look at this difference in cost just to move the tolerance limits just a little bit like this. So I think that this is a really good example of the difference between the Western way of thinking and the Asian view, so to say. Actually, in our company, that is Mycronic MyData, we have been working in Asia for many, many years, and have been really learned this lesson. And also, a lot of people in Mycronic have learned the lesson of the different view from our way of thinking and the Asian way of thinking. It costs a lot of extra work because specification doesn't matter. What matters is that you have to be a target. That's the main message. So, just to exemplify this, I will show you a very nice example of a process. A lot of people in this department is talking about processes. And this is a little bit of a special kind of process. So, that is the photomask process. Everyone that have bought a TV today, a flat TV, this TV has been developed and produced using this process. And actually, the photomask itself, that is the, so to say, the original that is used by some companies like Samsung, Sharp, and LG, they use photomasks. And our customers are doing this photomask. So I will tell you a little bit about the photomask process. Okay. You see here, actually, it's quite straightforward. You start with the mask blank, and the mask blank is a piece of glass, or quartz glass, actually. It's quite large. It's very, very big. Actually, this number is a little too small. It's almost close to 2 square meters today. And it's a thick glass. It's a 16 millimeter thick quartz glass. And that is the starting point of this process. So, you start with the glass, you put some resist coating on it, and you clean it, and then you inspect it. First time, it's manually inspected. It's handmade. There are no machines. There are some systems that really can be used, but these machines are actually just verifying in some situations, but in the end, there has to be a guy standing there looking by his bare eyes, checking the mask for pinholes or other defective things in the photoresist here. If they found a problem here, of course, they can always strip off the resist and put on resist on the plate before, and then do the whole checking again. So that is actually what is done if there is a problem in this situation. Now, the next step here is exposure. And that is a really, really tough thing. It can take about 4 days to expose one photomask, just one layer. So after the exposure, you do a development, and then before you do anything more, you check the mask again. And there is actually where we come in. Because we have developed a system that we call the MMS 15000, I will talk a little bit more about that is used for this inspection, and we are measuring 2 things, absolute accuracy and also CD, critical dimension. Critical dimension means actually how much line width on the photomask varies over the whole surface. So that is one of the most critical measures that we use to develop MMS 15000 for. And also, of course, absolute accuracy, that is how much the pattern deviates over the whole surface, that could be very, very large, that how much it deviates to the Cartesian grid. In this here, you can still save the glass because you have the possibility to polish it and put on some new chrome. So there is, in the value chain here, there is an escape route here. And some company is using this possibility that if you take here, after the measurement, you can redo the plate, so to say, and start all over. After this step, you do an etching of the plate. And now you do a remeasure again. You verify more accurately because now you are measuring on the pattern itself, on chromium pattern, after the etching. So that system is used again, and in this situation, you can put on polish and put on new chrome. But that is a quite expensive process, as I said before. Yeah. What I'm going to do then, if this mask is okay after this, you have the possibility to ship it away. If we go to a step and show that accuracy, specification accuracy we are talking about today is about 200 to 300 nanometer, 3 sigma range over this whole plate. And the plate is quite big, as I said before. So we need to make something to do the system that can measure this. I will talk about that later, but also the last thing here, and this I think is very important. There are no defects at Tarbell afterwards, because this is a photo mask used in a production system that generates millions of TVs, not millions maybe, but so if there is one defect on the photo mask, that it's not accepted. That is quite tough. So if you look back then, we turn it 90 degrees and we can then see what this is really about in the practical life, so to say. And this is an example of what happens in costs. I can tell you the price for a photo mask, just the glass piece, could be as much as $1 million. Just the cost of one glass. So if you have to destroy this glass or ship it to a customer where you don't have done the metrology, it's a disaster from many, many aspects. And if you see here, this is actually the cost, how it affects during the process here. Of course, these are secrets from the industry, but as we have been working with this industry for many years, we have a quite nice, good figure of how the cost distribution actually is in practice. So you can see here that the first step here, you start with the cost of $1 million here, maybe, or maybe less, depending on the size of the glass. Then the exposure step is quite expensive because they use a really, really expensive system delivered from the Swedish company Macronic MyData, and it takes many days. So you build up a value that is quite high here, just the exposure step here. After this, you have to do inspections, and you can see the inspection costs a little bit because it takes a long time. And also the final inspection here, and the pellicle mount. The pellicle is a piece of plastic, small little frame on a piece of plastic, little plastic on a frame that is used to cover and protect the front surface of the glass. And only one supplier in the world, some years ago, now there are a little bit more, but that can do this really high quality cover and this plastic pellicle stuff. So it's a very, very expensive piece of the mask. So that is put on the last step here. And then they do a final inspection, and this final inspection is also done manually. There are some systems that can be used, but a lot of this work is done manually still in this industry. So you can see that the cost of the final product is about the double of the glass black. And that is a rule of thumb you can use in this industry. So they are quite expensive, these photo masks. So in this process, it's quite clear that metrology in several steps here is the key for saving costs. It's so obvious that if you do a mistake here by just haven't done the measurement, or you have found defects, there are other systems used for finding defects. If you fail there, and the mask is shipped to the end user, like Samsung or LG or Sharp, as examples, it's a disaster. You are not allowed to fail in Japan. So if you send the mask that is wrong from the beginning, it's a big face loss. And the Asian culture doesn't like face losses. So after some years, when we have been in this area, there was a strong push from especially one of our customers that they wanted to have a metrology tool that could be used to measure these photo masks. So I will tell you a little bit about this tool and how we developed this machine. First of all, I want to show you this figure here. Actually, the metrology tool is built on the same principles as our writers. We also make writers, and that is the really big thing that we started with. So we have a lot of experience from our writing systems. What we're going to do now is that we're going to develop a machine that is able to measure also with very, very high accuracy over these large areas. This has not been done before, so it was a real challenge. There are some key figures here. What you can see here, you have a table where you put the mask on. You have a laser that is green today. In the beginning we used two lasers, one blue and one green laser in the same machine. And the reason was that Murphy's law tells you that when you have this very difficult mask with this thickness of chromium layer, the reflex will be zero because of interference effects. We wanted to change wavelengths. But today it's only the green light we're using. We have a scan width that we have an acoustic deflector here that is making a small little microsweep of 200 micrometer. We have a resolution in the system of a quarter of a micron. And the registration is not a word that maybe so many of you are familiar to. So I'm starting to change now. It takes a long time. You have to use the word accuracy. It's the same thing. But in our industry, we use the word registration. So everyone in our industry understands registration. They don't care about accuracy. So, but I'm trying to be a little bit more production engineer now to talk about accuracy. But that is the specification of this machine. 3 sigma over this large area. So, first of all, when you make a machine like this, the environment control is very vital. We are using very, very sophisticated materials. For instance, we are using Cerdur, that is very, very sophisticated glass for the table that has a temperature expansion of 0 in the 20-degree range, from 20 degrees to 23 degrees. We developed a new measurement method that we call random phase, and that is a special kind of way of treating, making images, making images in the time domain instead of the spatial domain that is normal for all CCD camera images. I cannot go into details. What we did was these 2 things. We had 2 fundamentally different hardwares to grab images in the 2D images. And the nice thing with this is that we could develop 2 metrology algorithms and or say methods that can compete. So we could actually find the best compromise of these competing algorithms. That was really powerful. We had to develop self-calibration, of course, because there are no references that we can use. We developed a method that we call set correction. That is a method to compensate for gravity. When you put a piece of glass on the table, the glass will bend automatically. You cannot avoid that because the back surface of the glass, or you can have contamination under the glass, or you can have particles under the glass. So we had to develop methods to compensate for this. But the most important thing was we did this with a very, very small team of people. We were on about maybe maximum 10 people doing this. Not any formal documents or anything that we had meetings and meetings and meetings. We just did your work. We met every second day for a half hour in the morning, and that was all. Maybe 1 hour. Okay. First of all, when we did this machine, we found quite soon that error budgets showed that it was not possible to do this. If you just do an error budget, we're using some models and so on, you see that it was not possible. But we felt it was possible because we have some experience from our writers. The most important thing, I think, learning. We did the development we don't have the information from the beginning, so you do the development and then you test and see in reality from the different steps. So that's what's the way we developed this machine. And I used to say that the whole development process is about cutting trees. If you really want to go down to a very, very low level of accuracy, you have to start with the biggest tree first. It's very obvious. So I want to show you this little graph here, and this is really true. This was the way it worked. To go from 250 nanometer to 120 nanometers in absolute accuracy, it took only 1 month. It was easy. It's trivial. In that situation, we were forced to delay delivery for 3 months. Our boss called our customer and said, oh shit, we cannot deliver the system because we cannot fulfill the specification of 90 nanometer. So we delayed it for 3 months, and we were struggling with these trees for about 3 months until suddenly we came down to 50 nanometer, absolute accuracy. So that was really, really tough. And so we couldn't deliver it in time, but we did it, and that was really, really nice. So I'm just going to show you some results. These are repeatability. That means that you do a measurement of a large plate on the stage, and you let it be on the stage, and then you remeasure it for maybe 24 hours or so. You generate a lot of measurements. Each measurement takes about 45 minutes. It takes 45 minutes just to measure this matrix of measurement marks here. And then if you compare 3 measurements, you can see that the mechanical stability is quite good. This is 3 sigma values of deviation between 45 minutes measurements. So it is possible to have a very, very precise mechanical machine that are able to, is so stable so it generates repeatability numbers in this range, 10 nanometers. So it is possible. But the most, the first thing is of course very important. But the last thing here is the real thing that counts. This is the absolute deviation to the Cartesian grid. These are 4 measurements. When we start with the 0-degree measurements, and 90-degree, 180-degree, 270-degree, and 90-degree measurements. You do measures so, and so to say, with the same golden plate or artifact, the reference plate. And when you back rotate this, and then you compare each measurement, then you calculate the deviation to the Cartesian grid. And that is around 50 nanometer over this area. And so far, no one has beaten us in this. So, first of all, of course, repeatability is very, very important. But the next step is, in the registration, you cannot do good registration if you don't have good repeatability. Because in this step, you are actually doing a real calibration to the physical God coordinate system, the Cartesian system. Okay. So, we are now going to advertise a little bit. We need people from KTH. And we need these kind of people. People who likes very, very complex systems. We're not only making writers, we also make inkjet systems and pick-and-place machines in Macronic, iData. So there are a lot of different disciplinaries that we actually work with here. We also do large area direct imaging systems. And that is one of the most cool products we are doing today. I used to call it a helicopter. I don't have any time to talk about that now, but that is a real cool machine. We do a lot of servers outside, and we do sales. We need people working all over the world, actually, in Asia especially, and also United States. And these people should be very educated because it's very complex systems, very, very high level. But I think this is the most important thing. We like people that like hands-on. This is not a work that you just sit behind the computer. You have to work with the machines. Sit and work and really understand how the machine works mechanically. And you probably are not going to do that in Sweden. You are probably sitting in a place in Asia with a customer screaming at you to finish your work every day. And I think that a lot of people in Macronic have gone through this hard school. But I can tell you, after this learning session, then you know what you are doing in this area. So, that was all for me. I think I made it in time.
Yes.
Thank you very much.
Peter. I think what you present here is quite important to the whole area. As we go towards automation, the need for quality control or process control increases. And if we look at the electronic industry in particular, the cost of process control equipment and quality control equipment is exactly the same as the cost of assembly equipment. It's a one-to-one relation. And this is one of the reasons why I will try to explain in the afternoon, and it's provocative. I think flexibility is dead. Okay? We cannot afford machines that do many different things fairly well. It's like you say. We need machines that do exactly what needs to be done. And if you come back after lunch, we'll try to explain that a little bit more.
I have
So-
a little small comment about that. You're talking about production system.
Yeah.
Our machines are actually producing mass, our writers. And the price tag for these machines is in the range from 15 up to 20 million US dollars. And the metrology tool for verifying this costs only 3 to 4 million US dollars. So that is the problem. People doesn't pay for metrology, not yet, because they are not realized how important it is. But I can just give, this is facts from the industry.
Okay, thank you to all the speakers.